All right, guys. So the other day we spent time kind of looking at this, and remember we said that M1V1 and M2V2 just represent first quantities versus second quantities. So today we're going to talk about what a stock versus a dilute solution is. It should be common sense. It should not be difficult. And remember I told you to also add another one in here if you do not mind. Does anyone remember what it was? Very good. Okay. So MAVA equals MBVB. So the way we deal with this is we treat it just like it's any old regular formula. If you have 3 of the 4 variables, can you solve for the missing one? Yes. Okay. I'm going to go ahead and tell you guys. There's also an explain part to these questions. Explain how you would do the following. Okay. Now, what does the A and the B represent? The one we just wrote. No. Acid and base. Okay. And I said that when we will use this when we get into what? Titrations. I remember this now. You guys were already packed up when I was writing all this down. Yep. Yep. Okay. So MAVA equals MBVB, but we're not going to talk about A's and B's today. We're going to talk about S's and D's. Okay. Now, S stands for what? Stock, and D stands for dilute. Here's the most important thing that I have to stress to you guys is put a big, huge star beside that last bullet. When you have 2 different concentrations given to you, the one that is the more concentrated, which will be the higher value, will be your stock solution. Does that make sense? Okay. Can the stock solution be written last? Yes. You just have to find it. Now, here's the ones where they really throw you for a curve, where they do not give the volume directly related to the molarity. You have to actually read it for comprehension, where they just word it in a really odd way where the volumes and the concentrations aren't side by side. So let's kind of look at a problem. So dilution. More? Okay, I couldn't see. It is not practical to keep different, it is not practical to keep, it is not practical to keep solutions of many different concentrations on hand, so chemists prepare more dilute solutions from a more stock concentrated solution. So instead of me having 9 or 10, just go ahead and tear it. Just go ahead and tear it off. Okay. Just go ahead and open the whole thing. Thank you. So instead of me having 5 or 6 or 7 different solutions in the back, I can have one. And what can I do with that one really concentrated solution? I can dilute it every single time. So that's what we're going to do. So tools for dilution, and these are some tools of interest that we're probably going to need. Okay, a pipette is a device for accurately measuring and transfer a given volume of solution. You already know what those are. Okay, that's not a difficult thing. A measuring pipette is used to measure volumes, which a volumetric pipette is not available. And then a volumetric or transfer pipette measures only one measurement. I'm going to go ahead and tell you. The volumetric or transfer pipette we do not have. So if you want to just kind of scratch that, or you write at the bottom and say do not have, do not use, won't use, we will never use one of those. Okay? Yes, we're going to use the measuring pipette. Now, here's what I need you to also make a note of. There is another name for this thing that I'm more than likely going to use. Okay? There's 3 different types of flask, right? Okay? What is the fancy flask with the narrow neck that we talk about? Yes. Yep, there's an Erlenmeyer flask. This pipette is named after someone. Moore's pipette. You were close. You're very close. It's his. It is what's that word called? Possession. It's possessive. Okay, it's Moore's pipette, as in it's his pipette, Moore. Okay, Moore's pipette. So here is what a picture of it looks like. As a matter of fact, Ryan Howard, do me a favor. Back left corner, you have to open the right cabinet first. You listening? Turn the right handle up and pull the left one open. And about eye to neck level, there's going to be a box full of stuff, of like glassware. Eye to neck level, maybe chest level. Do you see a box full of like glassware? Reach inside and grab one. Nope. It's in boxes. More left. Yes. Just grab one out. Yep, one of those. Okay? What he's fixing to do is he's fixing to walk around. He's going to show you a Moore's pipette. You guys know what the little plastic ones are, right? So the reason we're going to use Moore's is because it has the red word. It has graduations. So does it have a cap and gown? No, it does not have a cap and gown. Just hand it to her. Graduations. What are graduations on glassware? Graduations. It's a typo. Sorry, Chance. Add this to your list. Okay. Graduations. What do graduations on glassware mean? Markings. Okay. So they tell you specific amounts. So that is a Moore's pipette. And what you do is at the other end of it is you take a roller or a bowl. Okay. And you put it on the end. You remember those things when you were a kid, the snot suckers? You know what I'm talking about? You stick it up your nose, you squeeze the bowl, but it sucks the snot out of your nose. Okay? Yeah. What? Okay, so it's a glorified turkey baster. Okay, so this is, you put the bulb on the end, you squeeze it, you stick it down in your solution, you let the bulb go, and it sucks it up to a certain volume. Okay? Yes, sir. Yes. Okay. So the volumetric or transfer pipette, like I said, we don't have any of those, but that's what they look like. So notice what it says at the top. It says a calibration mark. Now do you understand why I say volumetric pipette? Do you remember the volumetric flask had that one little line that represented how much was in there? So it's the same concept, smaller version. Yes, sir. The bulb right here. I think it's so it's easier. Like once you get it up in there, it's easier to then read it once you get it at the top. It slows down the flow up. You put a bulb on the top, you squeeze it, you stick it down in, you let the bulb go, and it sucks the water up in there. Yeah. Okay? Now, on the booger suckers, they're not, but that one is. Okay? So, now, I guess I'm missing a slide here. Hold on. So, let's actually look at this first. So, let's look at this. Oh, you'll have to flip the page? All right, then don't flip the page. Go back. Huh? All right, so let's just go right here. So transferring solutions. Now, again, they're using a volumetric pipette, which is fine. We would just have to use the Morse pipette. So notice the left-hand side, they have what is known as the stock solution, and then they have an empty volumetric flask. True or false? True. What are they doing with that volumetric pipette? Notice the arrow. They're drawing the fluid up into the volumetric pipette, okay? And then they take it to the empty flask and they pour it in there. True or false? True. Now, would you agree or disagree? By the time this volumetric pipette was empty, would it be equal to or less than the value that was already in the stock solution? It's probably going to be less. So then what they do is, this was the stock. Again, we've taken some out of the stock, and this is going to be your new dilute solution. Visibly with your eyeballs. I know it's hard to tell on yours, but on this picture, how can you tell that it is the dilute solution? The color. Is it? Okay, well, cool for you. So, remember we talked about this. Now, again, you guys know how I teach in terms of these Velcro balls that I'm throwing at you. There's not two T's in transmittance. Give me 1 second. Okay. So when we get to absorbance and transmittance, now remember, are these the same or are they the opposite? They're opposite. Absorbent is how much light does not go through. Transmittance is how much light does go through. Okay. So in terms of a stock versus dilute, which one? Now listen to the way I ask this question. In terms of stock versus dilute, which one would have a higher absorbance? Why stock? It's bingo, there's more particles in there to absorb the light, okay? Which is you have a higher concentration, okay? But that's more accurate. So when we have these things, the dilute solution should potentially be a lighter visible color. Now, if the solution is colorless, well, obviously it's not going to be an issue. But if we're working with solutions that are going to be colored, then this is going to happen. And when we get to absorbance and transmittance, we're going to be able to visibly tell that because you guys are going to serial dilute a copper nitrate solution. Yes, ma'am. The solvent is the water. Yes. So this is the experimentation. Let's bring it up here. Yeah, put it back, actually. That'd be great. This is the experimentation. So this is me actually physically doing the dilution, right? Now, what if I brought Miss Furlong back over here and I needed you guys to tell her in explanation form how to perform this? Okay. Because here's the deal. Hint, hint, wink, wink. You're going to have to do it. Okay? So let's go back into the previous slide. So flip your paper back over. Now, I don't know why I've done this. I need to just eliminate this word. So I'm just going to white it out. Just... Whoa, don't break it. Okay. All right, so we're good. You can't see it. So here's what it is. Now, I'm going to be 100% honest with you. I think there's a slide missing, and I don't know where it is. But we're good with that. Is there a slide missing on here? Okay, all right. So I guess I got something out of order. That's okay. So here's the deal. We're just going to pretend that solution a minute ago, the stock solution was a 1 molar iron 2 nitrate. We're just going to pretend. Okay? So you would measure out the volume of stock solution, such as a 1 molar stock iron 3 nitrate solution, that was determined from the dilution formula, and place it in a volumetric flask with a size equal to the desired total amount. Now, that part that is in purple kind of sounds odd because we can make it a little more specific. True or false? True. With the size equal to the desired total amount. That doesn't sound right. What would you want to say to make it more accurate? The actual volume you need. Yes? Okay. So, the next part is this part in green. It says you would measure out the volume of stock solution determined from the dilution formula. Now again, could you make this green part and yellow part more accurate? What could you do? Give the precise amount that you calculated in milliliters or liters, doesn't matter, depends on how much we're dealing with, right? No, we're dealing with volume. Okay, very good. So instead of writing iron 3 nitrate, you could do that. But the one thing that I think is important that they do in here is they do tell you the concentration of the stock solution. Is that true or false? True, okay? So, again, we would need to know how much of the stock solution we need and how big of a flask we're going to put it in. Now, if you say flask, that's still kind of wrong. What kind of flask? Volumetric. So let's move on. Next, you would fill the volumetric flask to the mark on the neck with de-water until the meniscus is reached on the flask. Does that make sense? This is just like the last one, right? So the only difference between a dilution and a solution is that with the solution, you're starting with what unit? Grams. With a dilution, you're starting with a molarity and volume. Does that make sense? Yes, no, maybe? Now, the very last sentence is also left off on this. What's the last thing you always tell me? What you just made. This would make a whatever concentration, whatever volume, something iron 3 nitrate solution. Does that make sense? So this is going to be your reference slide. So I would circle this because we're going to come back to it. This is your reference slide. And again, it could be a little bit better, but it is what it is. Sir. Yeah, I mean, you would have to know the amount of the stock solution specifically. You would want to know the size of the volumetric flask you're using, and all that good stuff. And theoretically, if let's say that my stock solution is I need 500 milliliters, and my dilute solution I need 1,000 milliliters. Theoretically, could you know how much water you need to add to it to fill it up? It'd be 500, right? But I don't want to get that precise. I just want to say fill it up because it could be give or take. And that makes sense. Okay. Now, this is kind of an important thing to talk about. For making acidic or acid dilutions, it is technically okay to do the same process as the ionic solution, as long as the stock acid isn't too concentrated. And here's why. Sulfuric acid is the really bad acid about generating heat. And what that means is that if you try to pour a lot of water into acid, it's going to heat up really fast. What could potentially happen to the glassware that it's in? It could crack or shatter. If it shatters, you've got a mess on your hands, right? You've got sulfuric acid running all over you. Okay? So generally, go ahead. Yeah. Yeah. Trevor's on it today. All right. So let's just, okay, we realize there are two dangerous things. So generally, if you are doing the acid dilutions, and this is important, so I put a big star beside this bottom statement. Instead of starting out with an empty flask, start with about half of the amount of water you need to fill the flask. I'm going to explain that in the next slide. Okay? So, previously, I'm going to go back one slide. We had, look up here with your eyeballs. Okay? We had a stock solution and an empty flask. We poured the stock solution into the empty flask and then filled it up with water, right? If this had been a strong acid or a dangerous acid, instead of it starting with an empty flask, we would have had it, what? About half full of water, poured the acid in, and then did what? Then fill it up. And let's ask why. This is why. Okay? So, water to acid is wah or wah. Okay? Never, ever, ever add water to acid. And this is a ridiculous memory trick that I get you guys to know. I'm going to make it even stupider than this. Yeah. If you work at a burger flipping joint, if you do, awesome, you're making money. You're better than 90%, 51% of the population in this country. 49. Get it right. About that, yeah. Yeah, that's how many people are American food stamps. But sorry. All right. So if you were going to fry some French fries and you have a bag of them, what do you do with a bag of fries? You tear it open and you dump it into the hot oil. You take it hand by hand, right? Yes. Okay, you put the fries in the hot grease. Either you pour them in or you put them in the basket and set the basket down in there. Yes. Okay? Or the alternative, you take your bag of fries, take them on the floor, and you just pour the hot oil on them. Okay? So the problem is that that's a really bad idea. So we're going to add the fries to the hot oil, not the hot oil to the fries. So this is what this is. We're going to add the fries to the oil, not the oil to the fries. So we're going to add the acid to the water, not the other way around. Okay, well, it's not. All Well, it's not. Okay. So, if you do acid to water, everything's nice and good. Okay? Because here's why. What's going to happen is that when you try to think about if you have a volumetric flask, and let's visualize this. Okay? I really wish this Promethean software had like chemistry lab things I could add on to it. That would be sweet. I'm not paying anybody anything. Alright, so let's pretend that we have 250 milliliters of H2SO4. Okay, that's the only thing in this thing. Okay, and it's a 500 milliliter volumetric flask. So here's your 500 milliliter mark. If I take water and I begin to pour, and I'm going to take D water and pour it in there, do you agree there's a lot of acid in here? Okay, so you're only going to slowly increase the amount of water, right? Well, every time a water drop hits that acid, what's going to happen? It's going to start to heat up because it's an exothermic process. Well, the more and more water you add, the more and more heat's going to happen, right? And what's eventually going to happen to this glass? It's going to crack. Okay. The alternative way to think about it. What's up? Yeah. Let me make sure there's a pin in here. Start with a small stack first. Hold that. You can close it now. Alright, so if we start with about 100 milliliters of water, and then we pour the acid in there, is there enough room for that sulfuric acid to kind of dissolve into the water? Yes, okay, so that's going to dissipate the heat. And then, once we put our 250 mils of acid in there, okay, then we can fill the rest of it with. So the original water kind of dissipates the heat. I don't know. Because there's a lot more acid than there is water. Well, when you pour the acid into the water slower, it has time to absorb the acid. It absorb the heat. Yeah, you could. But if you just do it this way, acid to water. Alright, so dilution. Go ahead. All the acids. Doesn't matter. Doesn't matter if it's vinegar. Do it. If it says acid, do it that way. Acid to water. Very good. That's exactly right. Yep, that's right. Alright, so problem. What volume of a stock 11.6 molar hydrochloric acid is needed to prepare 250 milliliters of a 3 molar hydrochloric acid? Now, my first question is, and I'm going to ask this question a lot, if this word disappeared, if you did not see that, how would you know which one was stock? The higher concentration. Are we all on the same page there? Alright, so they say what volume? So what's the question? What volume? So, let's look at our data. We've got a concentration, a volume, and a concentration. So, two concentrations, a volume, and I need a volume. So, what formula are we going to need? Why couldn't any of what work? You could do 1 and 2. I think it's already typed 1. What's the problem? I have two concentrations and a volume, and I'm looking for a volume. Does that make sense? Okay. All right. So, here's the deal. Let's reread the question. And this is important. We know we're solving for one of the volumes, but it's key to making sure that you know which volume you're solving for. So, what volume of what? Stock. So, we're solving for VS. Now, my problem with you guys is I hope that you can do the basic algebra that takes to rearrange this thing. Yes, just algebra. Question? Okay, gotcha. Now, once we have this, we now just plug and chug. My question to you is, and this is where everyone every year kind of gets real flustered. What does molarity stand for? Moles over liters. What is your volume unit? Milliliters. So I'll ask you this question to give you some good news. Do you have to convert it? Stay with me. Don't write anything down. Stay with me. Now, I know that brackets represent molarity, even though I left them out. So, as far as units go, what happens? What happens? The molarity cancel, leaving me with what? If I had converted it to liters, would it make any difference? Not at all. So my question is, if your units cancel, does it really matter? Sure doesn't. If it makes you feel better, you are absolutely welcome to convert it to liters. And in fact, I have some students in the past that they didn't care what it is, what it looked like. If it had milliliters, they didn't even keep reading the question. They stopped right then, boom, and changed it to liters. And it made them feel better. And I'm fine with that. But I'm letting you know that you don't have to. Go ahead. If you did the math and you found the volume, if you changed it to 0.250 liters, your answer is going to be point something 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 liters. Convert that back to milliliters. Your answer would be the exact same. It would be in different units. Do you understand? Like, for real? Okay, so I want to make sure. That's why you don't technically have to. If you did convert, your answer would be numerically different, but unit-wise is the same. Okay? No, you would just put the solution. It would be hydrochloric acid solution. Okay? All right, so what would your value be here? Pause real quick. Significant figures. What would you say? 2. The reason why is because 3.0. 65. So 65 milliliters of HCl. And again, if you want to be even one of those fancy pants people, draw AQ behind it. Sure. Everybody cool with that? All right. Yes. No. I know what you're talking about. So, next question. What would the final volume of a solution be if 50.0 milliliters of a 0.5 molar solution of NaOH is diluted to 0.0125 molar? Now, there's a lot going on in this question. Okay? My first question is, what's the question? Final volume. Okay? So, then let's look at the data. I've got a volume, a concentration, and a concentration. I'm looking for a volume. So what's our formula? We all good with that? Now, the question is, what is the final volume? So in the dilution process, what's the final stuff? The dilute or the stock? The dilute. So we are going to be looking for the volume of the dilute, which is MSVS over MD. Now, again, the second thing that always throws students off in doing this is how they word the question and which numbers go in which part. I think you could do this. The algebra is fairly simple, but every year I get kids plugging in the wrong numbers in the wrong places. You have to make sure you understand what goes where. So let's start with our first number. If what would the final volume of the solution be if 50 mils of a 0.5 molar NaOH is diluted? Do you agree that's an action? So if something is diluted, then what does it start out as? The stock. Very good. So the molarity is 0.500. The volume is 50. Do I have to change it? No. And then I'm going to divide it all by the diluted concentration, which is 0.125. So 0.5 times 50 divided by 0.125. Now, question, how many significant figures are in this? 3. Tristan? Very good. That's a very good question. So the way you know it's stock is because 0.5 is greater than 0.125. All right, everybody got an answer? I love it. 200 milliliters. My bad. Sure. Yes. And here's why. According to significant figure rules, decimal point present or absent. Absent, start on what side? The right. Go to your first non-zero. But this is a weird case because what does that bar represent? It makes it significant. So you start with it and count it and everything to the, which makes it 3. You with me? You with me, right? You got me? You're getting it, right? Okay. It's amazing how it builds, isn't it? You're seeing both sides of it now. Sir? Nope. I take that back. Yes, the decimal point is preferred. Okay. All right. 300. You do this on your own. Matter of fact, do that. Matter of fact, do this one and the next one on your own, and notice the first word of the second question. Explain. Okay. Do those two by yourself. All right, so let's go ahead. If you haven't got the explanation part, we'll finish that in a minute. I don't want to spend a whole lot of time answering this one because that should be straightforward. It says 30 milliliters of NaOH has a molarity of 1.25 molar. The original volume was 250. What is the original molarity? Now, they throw this word in there, but instead of them using that word, what word could they have used? Stock. Very good. So original is saying the exact same thing as stock. So we were solving for MS. True or false? True. I'm not going to show you the math, but what was your number of significant figures? 3. Be very careful here. Look up here in the problem. How many is 300.0? That is 4. What is 250.0? 4. So why is your answer 3? Very good. And what was your answer, everyone? All right, very good. Now, let's move on to the next one. Now, this is just what I told Madison, and I want to make sure everyone understands this. Just like when you're making a solution, there is mathematical application to the diluting of a solution. When you are creating it, what was the math you had to solve for first? No. When you're making a solution, not diluting, making it, you got to have grams first, right? Well, with this one, you've either got to have a volume or molarity that's unknown. Okay. You have to, instead of grams, you have to have a volume or a molarity in this one. And they randomize how they ask that. Most of the time that I've seen these questions, they ask for the volume of the stock solution that you have to pipette out. That's normally what they ask. Again, it's not always, but normally. Question? Yes, let's do the math part first, okay? Okay? So, explain how to make 250 milliliters of a 0.1 molar NaCl solution from 350 molar solution. They never use the word dilute, and they never use the word stock. But how can you tell with your eyeballs which one is the stock? So because this number is higher, this automatically becomes the S. And they give you how to make 250 mils of a 0.1 molar NaCl solution. Those two things go together, true or false? True. So this and this is going to be your what? Dilute. So what are you technically solving for? Volume of the stock. Is that not what I just said? Most of the time they ask you for that. It's not always, but most. So we need VS, which is equal to MdVd over MS. Again, I'm not going to plug the math in, but what was the volume that you guys got? 71.4 milliliters of NaCl. Okay? All right, Jamila, go ahead and read me your answer. Now, I may pause you and add a few things. Pause. All right. My first question would be, and I'm listening from the perspective of, if I had all of the tools in front of me, could I still do it? So what you just said is you would measure out that amount and pour it into a certain size volumetric flask. Here's my question back to you of how to make it more accurate. What would I use to measure it out? Does everyone agree with that? Very good. Now let me ask you this. Could you use a graduated cylinder? Absolutely. If you wanted to throw a graduated cylinder in, that would be fine. In fact, in this case, did anyone even recognize how big that Morse pipette was? Anyone notice? It was 10. How many times would you have to use it? 7.4, 7.14 times, and that's a lot, right? So, or you could use a 100 milliliter graduated cylinder. How many times? One time. What would you rather do? 1 or 7.14? Of course you jerks would. I'm going to use the graduated cylinder. Okay, but Jamila, does that make sense? Okay, all right, go ahead with the rest of it. Perfect. Love it. Can anyone make it a little different, a little better? Okay, I like what she said. Go ahead and ask your question. I would have used a graduated cylinder, and here's why. Because it's 71.4 milliliters. And I want you to think about, if I wanted to measure the distance between me and the back of the room, would you use centimeters? Shut up and answer it right. Would you use centimeters? No. What would you use? Meters. If you have a 10 milliliter Morse pipette, you'd have to do it 7.14 times. Or you could use a 100 milliliter grad cylinder once. So I would have used, you could use your terminology that fits your tools. Morse pipette. Initially? Yes, that was the thing I thought I missed in the beginning. Is you would have to measure out 71.4 milliliters of a 3.5 molar sodium chloride solution. Justin? Yeah. Yeah, it is sodium chloride, yeah. Gotcha. Okay, go ahead. All right, now let me ask you this. Why do you not have to put the water in first? It's not an acid. Okay, does that make sense, though? Okay. Okay. Yeah. Very good. Now, just let me ask you this. Technically, are you wrong by doing it that way? No, you're not. He's absolutely not, because are you still going to create the same exact concentration and volume solution you need? Yes. You're just adding steps that you wouldn't necessarily have to add. It's you filling it up to 100, pouring it in, then putting the 71, and then filling it up, or pour the 71 in and fill it up. Do you kind of see the difference there? So again, you only have to put water in first if it's an acid and acetone. That's fine. Madison, go ahead. No, 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 no. Not mass. Measure. Okay, so I want to make sure this is measure, not mass. Yes. Volumetric flask. You would pour the 71 mils into the flask, and then you would add deionized water up until it reaches the mark on the neck. Jamil? It would have been right. You're good. No. Dustin? Absolutely. Tristan? That sounds right. Got it. Okay. I didn't even catch that part, but yeah, I see what you're saying. Till it reaches the line. All right. Next question. Let me look at this. Okay. No. You did just dilute it. By pouring the water in, it dilutes it. Does that make sense? If I need to dilute a jar of sweet tea, I would take some of the original sweet tea out, right? And then pour water in it. That's diluted. The very last statement should have been your diluted, your very last statement should have been, which would make 250 milliliters of a 0.1 molar NaCl solution. That 1 molar is less than 3.5. So that last sentence tells you you just diluted it. But what if it overflows your jug? All right, we're going to skip that one because it's too easy. Let's go to this next one. You can do it if you want to do it. I'm not wasting time. So the next one. In an effort to conserve lab materials, assistants combine 2 bottles of sulfuric acid. One. All right. Now, dude, what did you do before you got in here? Like, you are either, like, dead silent or a giggly little girl. All right. One bottle contained 350 mils of a 3 molar solution. The other bottle contained 1.5 liters of a 1.25 molar solution. What is the molarity after the assistant is done mixing the bottles? Now, I know what you're going to say. That this sounds a lot harder than it is, and there is one part of it that is going to be challenging. Here's what scares me. You're just going to want to multiply the multiply the concentrations and add the volumes, and you think that's going to be the right answer. That's not going to be the right answer. Say it again. All right, well, that's one problem. So since you've already brought that to our attention, let's go ahead and adjust. We've got 1 milliliter and 1 liter. If we are not sure which one to use, which one is always the better one to choose? Liter. So let's go ahead and do that. So let's change this to 0.350 liters. We're not sure, but we know that now they match, and that's the better unit to have it in. Okay? Stop. 0.35. 0.35. 350. 0.35. I'm not worried about that. It's point. Yeah, you should add another 0, but I'm not worried about that because I know the bottom line is going to be 2 sig figs either way. Okay. Now, the next part is what's the question? After the molarity, after mixing. Now, I need to ask you this. This is important. We know that molarity is equal to what? Now, let's start with the easy part first. After mixing bottle A, bottle B, we pour it into bottle C. How do you find the volume of bottle C? Add. Wow. Thank you. Okay. So, add. I need the volume. You add the volumes. Yes. That's the easy part. Now here's the deal. Exactly, I'm looking for molarity. So I know what you're thinking. Why did you throw this whole mole thing up there when I've already got 2 molarities up there? Here's the deal. Molarity represents moles per liters. What is the mole? It's an amount of substance. So I'm trying to find how many particles are now floating around in the solution. So can I just take my molarities and add them together? Because molarities represent mole per liter. Can I just multiply my molarities? No, that's mole per liter. I need my number of moles. So what I need, and this is the important part, I need liter total and moles total. Now, this now becomes a little bit simpler of a problem. I need moles of both bottles. Bingo. But how do I find moles of each one of my bottles? Very good. So, let's say bottle 1, and that I'm just going to go in order. So we would say it is 0.350 liters times 3. And then I would say bottle 2 is 1.5 liters times 1.25 molar. And then when I get those numbers, what do I do with them? I add them up. Does that make sense? Now you do know you know what B1 and B2 is, right? Bottle 1, bottle 2. Okay. So what I'm going to say is bottle C, or bottle, why did I say C? Bottle 3 is my total. Okay. So again, this is a tough question, but if you think about what the question is, the question was, what is the molarity after it was mixed? After mixing, you took 2 solutions and poured them together. So when you're calculating molarity, do you need to know how many things are floating around in a certain volume? This is what we're doing. We're finding out how many things, which is what unit. Moles are floating around in a certain volume, which is what unit? Liters. Okay. So what's your number of moles for the first one? 1.05 moles. And then what about your B2? Yep. It's the least number of decimal places. Well, what about both of those numbers? Same number. All right, so that's 13, that's 9, and that's 2. So 2.93 moles. All right, so what is your new concentration? Hold on a second. We rounded wrong, guys. Let's go back to bottle 1. What should be your number of moles in bottle 1? No. 1.1. Okay, well, fine. We'll go back with that idea. Bottom line, If you wrote 1.6 or 1.62 or 1.5 or 1.59, does it really freaking matter? No, you're plus or minus one significant figure. If you're at 1.567, you're good. If you put 19, you're bad. Okay? That would be wrong. Shut up. Okay? All right. Perfect. 1.62. Sounds great. All right. Now, this is another tough one. These are the types of questions that you guys got to get used to. The other ones are baby questions. These are legit. In a lab neutralization. Now, above the word neutralization, write the word acid-base. Anytime you see the word neutralization, that is code for acid-base dilution. Neutralization, neutral, right? We're trying to neutralize an acid and a base. So that's what tells you you're in the land of A's and B's. You neutralize it. Yes. Yeah. Okay. In a lab neutralization reaction conducted between, what's that say, 4 point something? 4.5 molar hydrofluoric acid. Now again, question, is that strong or weak? Weak. Now, I'm not talking about dangerous or safe. I'm talking strong or weak. Remember we said hydrofluoric was weak because it's less than 100% dissociation. And a 3.2 molar barium hydroxide. How many grams of the salt product would there theoretically be produced if you combine 450 milliliters of the hydrofluoric with 672 milliliters of barium hydroxide? Here's the first question I want you to do. How much time we got? Yeah, we should be able to have time to do this. My first thing I want you to do, and nothing else, write the balanced chemical equation for this. Let me give you one hint, and I've taught most of you this, and this was in the summer packet that you guys did. All acid-base reactions produce a salt and a water. Go with that idea. Remember, acid-base reactions are just like double replacements, where they create a salt and a water. All right, so we've got HF, again, acid plus a base. Now, is barium hydroxide strong or weak? It is strong, and acid base always produce a salt and a water. Now, remember I told you this trick. If you've got a hydroxide on one side, how can you write water? HOH, which makes it a lot easier to balance. And then the salt, just like the double replacement. Barium hooked up with who? Fluoride. Is that a brand new compound? What do? Check your charges. So that's why you got BAF2. And this becomes a really simple thing to balance. You put a 2 here and a 2 there. Okay? All right. Now, we've got this part done. What is the question? Grams of the salt. So I'm trying to get to here. Do you agree that's my question? Now let's figure out what our data is. So it says you have 4.5 molar hydrofluoric. So 4.5 molar of this. And I have 3.2 molar barium hydroxide. Would you agree or disagree? Okay. Now, and then it says you have 450 mils. Now, we've already got concentration, so what can we do with that? Let's get into liters. 0.545 liters. All right. This looks familiar. And this question is kind of out of place, but I think it's a good point to throw it back in there. My question to you is, do we even need MAVA equals MBVB? Why not? Do I need a molarity? Do I need a volume? I've already got both of them. I've got MA and VA, MVB and MB. Does that make sense? I don't need either one of them. I'm trying to get the grams the other side. The chance you've already told me what I do, but let me ask this question. I've got to get from one of these reactants to the other side. Which one do I pick? Find the limiting reactant first. Now, my question to you guys is, you should know this. The cheat is limiting reactant equals what? Now, I'm going to be honest with you guys, and I told you this a long, long time ago. You're going to run into this stuff with the limiting reactant with volumes and concentrations. And I told you, if you embrace the concentration and volume, you will much more prefer this over grams. You know why? Because grams, you got to find the mass, and that's a pain in your... It rhymes with mass. Okay? So if you got to find the mass, it's a pain in your... You with me? So all we have to do with these two values are what? Multiply them. So, has anyone already done that? All right, what is the first one? Y'all can't see that color. 2.5 what? That's okay, that's sig figs. And that's moles. And then what about the other one? Now, from this point, what do we then do? Divide by the coefficient. But let me ask you this. Yes, you need to show it on that day. May 1st, yes, you need to show that step. With your eyeballs, do you even really need to plug it in? No, because 2.5 divided by 2 is definitely going to be less than 2.2 divided by 1, right? So, we now know that HF is our what? Limiting reactant. This is the part where I expect you to be able to go from here. Can you go from moles of HF to grams of BAF2? Yes, you got to find the mass. It's a pain in your derriere. Okay? So I'm going to let you guys finish that up, and I'm going to stop the video. What's wrong, Jimmy? Go ahead. All right, do you agree that I'm going from HF to BAF2? Okay, I'm in moles, correct? All right, if I need to go from HF to BAF2, what must, matter of fact, I'm going to go ahead and write it over here. So I've got, it's 2.5, right? Yes, okay, 2.5 moles of HF. I know I don't want this anymore, right? Tell me how to get rid of it. I eventually got to get to BAF2, true or false? What is the only way? What's my bridge from one side to the other? You with me? No? We've done this hundreds of times. The only way to get from one compound to something completely different is your mole to mole, right? Now, why can't I stop here and give you an answer? No. What's the answer needed to be in? Now, why can't I stop here? Because you have to get it to what? Now, I don't want moles of BAF2, so put it on bottom to get rid of it, right? Dustin's already got it. Dustin, what's the mass? 175 point what? Now, what is your mole to mole ratio? 1/2. Yes, that's your coefficients. All right, so what's your final mass in grams to 2 sig figs? $220. Sir, yes, sir. Yes, sir. It's 19 even. So it's 19 even, so it's 38 total. We have one problem left, dad darn it.